So, lecture 5 continues, trying to get reactions and pending moments in different loading of beams, or simply supported beam, different loading. Now, this beam is loaded trapezoidally. The shape of the load is a trapezium. Unlike the one we just did previously was loaded triangularly. So this is loaded trapezoidally, just like I said. In such a beam and in such type of loading, the total load is the area of the shape. In this case, the area of the trapezium. So to get the reaction, I want to get reaction A. So I take moment about point B. I think it's equal to 0 because it is. This is the support. So I have 7 RA. Now the load, 7 RA. I will see that if I take the area of this triangle, area of this trapezium straight, I may find it a little difficult to get the center of gravity of the trapezium. So what I will do is to divide those shapes that are easy for me to get the center of gravity. That's rectangle. Rectangle, this is C, this is D. Rectangle ACDB, this is E. I divided to rectangle ACDB and the triangle CDE. ACDB, rectangle. CDE, triangle. I've divided load. So the two shapes now, that is rectangle and triangle, are easy for me to get the center of gravity. I could get the the area of the trapezium, but it may take some time to get the center of gravity. So in order not to waste that time, I decided to divide it into two shapes that are easy for me to get the center of gravity. So I can now calculate the load and the moment that the load generates. So that means minus, I take the first one, ACDB, that's the rectangle. The intensity at the beginning here is 2. So the area of the rectangle is 2 times 7. 2 times 7. Then times the distance from the center, because the center of gravity of a rectangle is from the center, which will be times 3.5. So that's one of the loads, creating a moment. The next load is a triangle, minus the triangle, the area of the triangle, which in this case, you see, the intensity here, the total intensity here is 5. And if the intensity from D to B is 2, that means from D to E is 3, to give you that 5. So for the triangle, the area of the triangle is 7 times 3 over 2. This DE is 3, because DB is 2. The whole of them is 5. So 7 times 3 over 2. Then to create a moment, to make that triangular loading a moment, to make it a moment, times from the center of gravity to B, which in this case is the 7 over 3. Now that is equal to 0. RA is equal to 14 times 3.5 minus 7 times 7, 49. That's 49 over 2. The 14 times 3.5 minus 49 over 2. That gave me 10.5. 10.5 kilonewton. That is RA. It's what the 10.5 kilonewton. So let me get RB. Reaction at B. So reaction at total moment at A is equal to 0. 7 RB. Turning this way. The load will turn against it about point A. So minus something. The load, I take the other load that is the rectangle, which in this case the area of the rectangle is 2 times 7. then making it a moment times 3.5. Then minus again, then the area of the triangle, which in this case is 7 times 3 over 2, to make it a moment from this the center of gravity to A, to point A, will be 2/3. It won't be 1/3 this time, it will be 2/3. So 2 times 7 over 3. 2 times 7 over 3. Which means it is equal to 0. So RB is equal to 14 times 3.5 minus this, minus 7, that's 49, minus 49, which is equal to 14 kilonewton. Is equal to 14 kilonewton. So easy. I've gotten the reaction A and reaction B. If you add the two of them, it will give you the load, which is the area of the trapezium. Which is the area of the trapezium. The area of the trapezium is 7 times 7 over 2. 7 times 7 over 2. We give you the area, and if you add these two, it will give you 24.5. 24.5. 7, 5. The area of the trapezium is 7 times 7 over 2. The length 7. The width 7 over 2. Which is 49 over 2. Which is 24.5. If you add 10.5 plus 14, it will also give you 24.5 kilonewton. That shows you are correct. That is adding vertical forces to see whether the moment you took was right in getting the reaction. So, having got the reaction, the next thing is to calculate bending moment. Now, to calculate the bending moment at A, M at A is 0 because of the nature of the reaction. To get moment at let's say the midspan, I have M at the midspan, turning this way, because I say it's positive. Turning this way, the reaction will be against it, so minus the reaction A, which is 10.5, making it the moment to that distance, to the middle, which is 3.5. So the load is turning with the moment, so it will plus the load down. The load this time is, the first one is 2. 2 times 3.5. 2 times 3.5, that's the total load, rectangle. Then making it the moment is half of 3.5 over 2. Then plus the next one, that is the triangle. This triangle at this point, at the middle here, I have to get this ordinate at the middle of the triangle before I can know the area of this triangle. That is, this is F and G. To get the triangle C, the area of both the area of triangle CFG and its center of gravity, I have to get the ordinate FG for me to get it by similar triangle. Characteristics of similar triangle is the equality of the ratio of sides. So in this case, I have the triangle CDE is similar to triangle CGF. So if that's the case, I have 7. Considering triangle CDE, 7 over 3, that's DE over 3 is equal to 3.5. 3.5 over GF. So, which means GF GF is equal to 3 times 3.5 over 7. That is equal to 1.5. 3.5 divided 7 is 2. 2 divided 3 is 1.5. So GF is 1.5. This is 1.5. So with that, I can now, the ordinate at the middle is 1.5. And if that's the case, I can now get the area. The area of the triangle, which is 3.5 times 1.5 over 2. So as a moment now, I now get 1/3 of the length, 3.5 times 3.5 over 3. 3.5 over 3 equal to 0. So the moment at the middle, the moment at the middle is equal to, if I send all this to the behind the sign of equality and they change signs, it will be equal to 19.907. That is 19.91 kilonewton meter. That is the moment at the middle. So I can get the moment at the end. That is the moment at point at the end. That which will give me that the moment at the end. What I've been showing here at the moment at B will give me equal to 0. So the draw dependent moment diagram, easy. If you look at it, it's a quadratic function. The moment is quadratic. So moment equation is quadratic. So this is A, this B. At this point, at the middle here, the moment is 19.907 kilonewton. That is 0 or 19.91 kilonewton meter. So it's a curve. That's bending moment diagram. That's bending moment diagram. If I want to get the shear force, it is simple. I start from shear force at point A. Is the reaction at A. So QA, the shear force at A is equal to 10.5 kilonewton. Positive up. At the middle, shear force at the middle will be shear force at the middle will be equal to 10.5 minus the load now. The load will be the area of this trapezium. The trapezium ACF. Let's say this is I. Trapezium ACFI. The area, which is, so this minus the area of this area, which is 3.5 bracket. This is 2 plus, this is 2 and 1.5, which is 3.5 all over 2. That's the area of this. So this minus that will give us the shear force at the midspan. Will give us the shear force at the midspan, which in this case I got it equal to, the shear force at the midspan is equal to 0.875, which I got to be equal to 0.875 kilonewton. That's shear force at the middle. Shear force at the middle. So, which is positive. Shear force at the middle is positive. Then shear force at the end. Shear force at the end. I got shear force at the end minus 14. I got shear force at the end, which in this case it is 10.5 minus minus 3.5, that's this, then minus this, the whole of this. Or I can handle the whole load together. That means this becomes 7 bracket 2 plus 5, the whole of them over 2, which will give me minus 14. That's the area of the trapezium, CABE, which is the length, which is 7, times the sum of 2 and 5 over 2. So at this minus 14 kilonewton, meeting force, the reaction A, reaction B, which is 14, closes. Minus 14 plus 14 closes to 0. So shear force diagram would be like this. If this is A and this is B, at A the shear force is 10.5. It starts reducing. At the middle, it was 0.875. It was reducing, and now get to negative 14 here. So it moves. At this point is 14 kilonewton. Positive, negative. This is a straight line, sorry. This is the way it was drawn freehand. So that is the shear force diagram. So we've been able to get both the reaction, the bending moment, and the shear force for this nature of loading on a simply supported beam. That is the end of this episode.